Hello my dears, in this lecture I'll discuss the famous resistance cube problem. This problem is generally solved using Kirchhoff's law, but here we will solve it using the method of symmetry or the symmetry rule. After solving this problem, I'll be telling you a mind-blowing trick, so stay tuned. So now, remember, in this resistance cube, since all the edges of all the resistances are of same length, so irrespective of in which format this question is asked, all resistance will be same. Have no doubt about it. You cannot have resistances R2, R3 or something like that. Every time you will be having similar resistances. You can have all resistances of 1 ohm, all resistance of 2 ohm, all resistance of 2R, something like that, isn't it? What we are going to do here is that we will solve it by the method of symmetry or symmetry rule instead of going for the Kirchhoff's law. Now, have a careful look at the diagram. This is a three-dimensional diagram. What I am going to do that I will try and convert it into a two-dimensional diagram. Now try to think. Think that you are looking at this cube from top, or you want to draw the top view. Remember, to draw a top view of such a simple network, you need not study engineering drawing and all, isn't it? You can have a look and draw the top view. So if you draw the top view, means you will be seeing only these four edges, because this node will be hidden, this node will be hidden, this node will be hidden, this node will be hidden. So in that case, you will end up drawing something like this only, isn't it? And all resistance will be appearing here, 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 here. So the point A dash, D dash, C dash, B dash will be marked like this, isn't it? A is just below A dash, so A and A dash will be one and the same. Means if you are actually drawing the diagram, that is you are seeing the top view, then it will look something like this, isn't it? So A dash and A are in line and you are looking from the top. You are just looking from the top, isn't it? So you will be seeing all these four edges and nothing else. This A dash and A will be at the same position. This D dash and D will be at the same position. This B dash and B will be at the same position. This C dash and C will be at the same position. That does not serve our purpose, isn't it? We want to see all the resistances at the same time. For doing that, what you do, you grab the upper part and squeeze it slightly. Think carefully. Grab the upper part and squeeze it slightly. In that case, these resistances will be spreading out, isn't it? And you will be able to see all the resistances when you are looking from the top or you are drawing the top view. What now you are going to see from the top will be something like this. See? This is what you are going to see from the top. All resistances are naturally, isn't it? So if you mark this point as A dashed, then this becomes B dashed, this becomes C dashed, and this becomes D dashed. Okay? See? A dash, B dash, C dash, D dash, A dash, B dash, C dash, D dash, and balance all resistances have a spread out. If you are not able to view like that, then what you do is squeeze from the top and then crush the cube completely, isn't it? You crush it, squeeze it, crush it. So these face will appear like this, these resistances will be appearing like this, and you can have a 2D diagram here. Okay? So A dash and A are in the same line, that is A is below A dash, So this point is A, this point is B, this point is C, and this point is D. Okay? What you are supposed to do, you are supposed to find equivalent resistance between point A and C. So you are supposed to find equivalent resistance between point A and C. Now go by the mirror symmetry. In mirror symmetry, what you do that you join the line which connects both the terminals about which you are supposed to find the equivalent resistance. So I am joining it like this. See? Join it like this, isn't it? Then draw a line perpendicular to this line which bisects the diagram completely, like this, isn't it? So we draw a line like this. Now see if one side is the mirror image of other side or not. If you are not having a mirror image, then you don't go by mirror symmetry. Use some other method, isn't it? So let us check. Supposing I am placing a mirror here, isn't it? So this resistance and this resistance becomes mirror image, isn't it? This resistance becomes mirror image. 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 So here we do have a mirror symmetry. Once you find the symmetry, so this line is also known as line of symmetry or a plane of symmetry. Since we have converted it into a 2D diagram, so we can conveniently call it line of symmetry, isn't it? Now you know that in mirror symmetry, this line of symmetry, actually all points on this line of symmetry are equipotential. It means that this node, this node, this node, and this node all will be equipotential. Equipotential means that no current will be flowing through this resistance or through this resistance. Am I clear? Let me repeat. Once you find the line of symmetry, here we are going for mirror symmetry. So we have joined the terminals about which we are supposed to find the equivalent resistance, and we have drawn a plane of symmetry like this. Since we are operating in 2 dimensions, so we can call this plane of symmetry or vertical plane of symmetry as line of symmetry also, no problems. In mirror symmetry, all points on line of symmetry are equipotential. It means here we are having this resistance here and this resistance here, and these lie on this line itself. So naturally, no current flows through this resistance, isn't it? For flow of current, you need a higher potential and you need a lower potential. Since these 2 nodes are at the same potential, so no question of any current flowing through this resistance or through this resistance. Hope it is clear now, isn't it? Now the diagram becomes extremely simple. See? Very, very simple, isn't it? What you do, you just remove these 2 resistances because they are dummy resistances. They are of no use in this circuit. Clear? Now all resistances are R, isn't it? This is a line which is just joining A and C, nothing else. So now try to think about the diagram. So let us mark this point as A. One resistance we are having here to here, isn't it? Then we are having a resistance like this. Then we are having a resistance like this. Then we are having a resistance like this. And this is the point C, isn't it? On the upper side, now we are having a resistance like this. We are having a resistance like this, isn't it? On the lower part also, we are having a resistance like this, 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 isn't it? So now you can easily see that these 2 resistances these two resistances are in what? Series. See? These two resistances are in series. So R and R are in series. So what is the equivalent resistance? So 2R. Isn't it? This R and this R are also in series. So what is the equivalent resistance? That is 2R again. Now this 2R and this 2R are in parallel. Isn't it? This 2R and this 2R are in parallel. So what is the equivalent resistance? Isn't it? So R equivalent is a straightaway 2R by 2. You simply remember the formula R by N of R equivalent in parallel. If N similar resistances are connected in parallel, then the equivalent resistance is given by this formula, that is R by N. Isn't it? So 2R, 2 times. Isn't it? So 2R divided by 2. That gives you straightaway R. Now, again read all the diagram. So now you are having R here. Then again you are having another equivalent resistance, that is R. Again you are having one more resistance, that is R again. Isn't it? So this part is complete now. Now think about these two, R and R connected in series. So you are having 2R here. If you feel, you can draw the resistances also so that you get comfortable. Isn't it? Something like this. Just to get a feel, otherwise there is no need while solving. Isn't it? So now you are having R and R. So this resistance is basically 2R. Same diagram appears downwards. So here also you are having 2R. So basically you are landing with 2R, 3R and 2R. All these three are connected in parallel, isn't it? You can see. So find the equivalent resistance. So these are not similar, so you cannot apply this formula. So find 1 by R equivalent is equal to 1 by 2R plus 1 by 3R plus 1 by 2R. That gives you 6R. So here you are having 3 plus 2 plus 3. So 3, 3, 6. 6 plus 2, 8 by 6R. So R equivalent is 6R by 8. That is 2 3s are 6, 2 4s are 8. So 3 by 4R is the equivalent resistance. Am I clear? Isn't it? So we have found here 3 by 4R is the equivalent resistance. So this is how this resistance cube network is solved using symmetry. Now let's come to the trick part, which I told you that I will be telling you, isn't it? Have you ever thought that in how many ways this cube problem can appear in the exam? Have you? No. Then try to think with me. See those cubes here. Isn't it? If you are having a cube, then try to think how many edges you are having. Isn't it? So how many edges? You just count them. 1, 2, 3, 4, bottom. 5, 6, 7, 8, top. 9, 10, 11, 12. So you will be having number of edges as 12. Isn't it? 4, 1, 2, 3, 4, then 1, 2, 3, 4, 4 plus 4, 8, 9, 10, 11, 12. How many body diagonals you can have here? Think about it. Body diagonal means you are connecting this point with this point, isn't it? So get hold of the back face of the cube and get hold of the front face of the cube, isn't it? Then join the opposite vertices directly, like this. This is front face and this is the back face. So this is the line which joins these both, and this line is called body diagonal. So how many body diagonals you can have? You can have 4 body diagonals. You can join this with this, you can join this with this, isn't it? And similarly here also, isn't it? So you can have 4 body diagonals. How many face diagonals you are going to have? How many faces are there? Front face, back face. So 1, 2, up, down. 2 plus 2, 4, left, right. So 6 faces you are having, isn't it? So in a cube, basically you have 12 edges, 4 body diagonals, and 6 faces. So 6 faces if you are having, then how many face diagonals you can have? On one face you can have one diagonal like this, one diagonal like this. So actually you are having 6 into 2, that is 12. So you are having 12 face diagonals here. Am I clear? In a cube, you have got 12 edges, 4 body diagonals, and 12 face diagonals. Sum it up. It gives you 28. It means that this resistance cube problem can be asked in 28 ways. Isn't it? Be sure. There is no 29th way, I assure you. Now, won't it be amazing to know the answers of all these 28 questions? Isn't it? It will be definitely amazing to know the answer of all these 28 questions, isn't it? You can simply see here, isn't it? You can be asked to find the equivalent resistance between these two, 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 so on, isn't it? Now, 28 questions, don't worry, I am not going to give you 28 answers to mug up, isn't it? As simple as that. But I'll tell you a trick so that as soon as you sit in a competitive exam and you see a question which looks similar to this cube, isn't it? Or resistance cube. In that case, just looking at it, you can simply know the answer or guess the answer. How? That's the trick, isn't it? Now think, whenever you are going to bed early, isn't it? Whenever you are going to bed early, which you don't do usually, then all your family members might ask you, isn't it? Early for bed, isn't it? So they might ask you, are you early for bed? So remember, early for bed. Early for bed. As simple as that, isn't it? This is my way of remembering. You can remember it like something else, like equivalent Facebook or something like that, isn't it? Now, what you do, simply draw a line like this. Put a ratio sign here. Getting my point? How I am doing it. Now you must be knowing counting, isn't it? You don't have to count much. You have to count 1 to 7. 1, 2, 3, 4, 5, 6, 7. That's it. That's the trick, isn't it? Once you put this ratio mark, then you start writing. 1, 2, 3, 4, 5, 6, 7. Over. You start writing from the denominator. 1, 2, 3, 4, 5, 6, 7. Isn't it? These are the answers of all 28 questions which can be asked. Isn't it? How interesting it is, see? These answers are for 1 ohm resistances. Meaning, irrespective of whether you are being asked to find the equivalent resistance about this edge, this edge, this edge, this edge, this edge, this edge, whatsoever edge, isn't it? The answer will be 7 by 12 ohms. If you are asked to find about the phase diagonal, meaning you might be asked to find the equivalent resistance between this, like this, isn't it? Okay. Or like this, any phase diagonal, the answer will be 3 by 4. If you are asked to find the equivalent resistance about the body diagonal, then the answer will be 5 by 6. So this is the trick. Simply EFB, mark the ratio sign, then count till 7. While placing, be careful how you are placing it, isn't it? Don't start 1, 2, 3, 4 and all nonsense, isn't it? You start from the denominator writing 1, 2, 3, 4, 5, 6, 7. Now, we have right now solved this question. So let us check whether this trick applies here or not. We found the equivalent resistance across AC. What is AC? Is it an edge? Is it a body diagonal? Or is it a phase diagonal? Clearly you can see it is a phase diagonal, because at the bottom face we are joining the opposite vertices. So it is a phase diagonal. So in the phase diagonal, if you are solving a question related to phase diagonal, irrespective of which phase diagonal you are finding the equivalent resistance, the answer has to be what? 3 by 4. Isn't it? See? This is for unitary method. All resistances are. So multiply it by R. So 3 by 4 R you are having here. If the resistances are 2R, multiply your answers by 2R. If all resistances are given 5 ohms, multiply the answers by 5 ohms. As simple as that. Can you have a trick better than this? I don't think so, isn't it? So, stay tuned for such tricks. I'll be seeing you soon. Until then, take care and be safe. Bye.